All right, guys. Let's take a look. So with my hint on number 1, did somebody figure out how to do that? Anybody? What was your first step? I'm going to leave some room. Leave some room. Is anybody concerned at the beginning that it was equal to negative 12? Good. Okay. That's fine. A few words. Okay. Also. Yes.
Would complete the square.
Complete the square.
Because you want the format x squared plus y squared equals radius.
Yeah. Well, I want. Yeah. Exactly. And they could be shifted. In fact, we know they're going to be shifted. So, what's complete a square? What's the 2 steps? Take this and cut it in half, and then square that. So plus 9, so I better add 9 to the other side. Most common mistake is to forget to do the other side. Poor little dude. Little tears. Cut in half, square it. So you end up with, and the beautiful thing about, this is not a difficult thing to factor, but if you get gross numbers, whatever half of this was is what goes in here, right? Half of the negative 6 was negative 3. Half of 4 was 2. And you get that. So what's the center?
3 negative 2.
Do it again, sorry.
3 negative 2.
3 negative 2. I like it. What's the radius? 1 is, in general, it's the square root of this, right? Because it's good old Pythagorean theorem, which we now know shouldn't be attributed to Pythagorean, but we'll work past that. Is that all right? Shaking off some dust. Now, here's what's interesting. How many variables are in that equation? In that equation? 2. So obviously, if I want to graph this, now, very obviously, if I said graph x equals 3, what's interesting is I would get some people doing one thing and some people doing a completely different thing. Well, how would you graph x equals 3? Okay, you would graph straight line. What if somebody just did a number line and put a point at 3? That's also acceptable, correct? So that's something I'm going to do later with you. That's going to explain a concept. It's not necessarily going to be computationally useful, but it's good in terms of understanding the concept. It's related to what we just said. If I go down a level in dimension and go up a level in dimension, it just kind of repeats. If I have no other information about the second dimension. So if x equals 3, y could be anything. So just repeat x is 3 forever, correct? Okay, hopefully you guys are kind of with me. So this is a circle. So real quick, watch this. This is so cool. What if I just add this? What if I just take out all the y dependence? You could solve this. You could square it out. You could take the square root. But screw that shit. Can somebody just tell me what x is just by looking at this damn thing? Could be 4 or, because I'm squaring, 4 minus 3 is 1 squared is 1. What else do you square to get 1? So a 2 would work also. You with me? So if I plot the answers, 2 and 4, is there not a center to them? What's in the middle?
3.
So the center is 3, and what's the radius?
1.
Holy shit. Now, there's no point to looking at it like this until you start talking about higher dimensions. Then we want to go back and go, if we wanted to, we could have talked about it like this, couldn't we? The center is 3, and the radius is 1. So I made you guys figure it out, but you could have just graphed it and figured it out. Are you guys kind of with me? Now, obviously, the more disgusting the equation gets, blah, blah, blah. But if it's in this form, center, radius. Why does it not make a circle? Because a circle requires how many dimensions?
2.
And I've only given myself 1. Now, if I add y information, I'm allowing myself to exist in the xy plane. So then if I have like x minus 3 squared, what was it, y plus 2 squared? Then I'm allowed to go out 3. So my center is going to be 3, negative 2. You can do it, Jeff. And then I'll go out 1, 1, and up 1 and 1. And I get my little circle. Whee! Okay. Did that kind of quick, hopefully it came out right. Now, dude, I really want you to understand. I'm stuck in one dimension of the first problem we just did. The minute I allow another dimension, the radius just stays one, but now it can rotate. So now I get a circle. So how do I get a sphere? What would the equation of a sphere have to look like then?
Z squared?
Yeah, it would be x minus 3 squared plus y plus 2 squared plus z minus 1 squared, whatever the hell equals 1 or whatever. You guys kind of with me? For the exact same reason. How are you guys doing? Now again, I don't think you've ever looked at that way, necessarily. It's interesting in terms of figuring out concepts, because we're about to expand everything you've ever done. We're going to allow it to live in more dimensions. So you're going to want to be able to kind of tease things out like this. Look at it in a way different than you have before. And again, what we just did is not necessarily going to help you solve any problems in the homework necessarily, but it explains the concept more fully. Okay, sorry. I do that sometimes. I have a shirt that says I go off on a tangent. Number 2, I really hope you guys didn't do a ton of work for this. Yes? No? I saw a lot of people doing by parts and such. What's the derivative of tangent? Tangent theta. Secant squared theta. So what's the derivative of cotangent theta? Negative cosecant squared theta. So all the co shit is negative from the non-co stuff. Yes? You guys with me? You guys with me? So what's the integral of cosecant squared theta then? Where must it have come from? Negative cotangent. Exactly. So if you know somebody's derivative, you automatically know the antiderivative. Right? So this one is just a straight up, do you remember your derivatives? How do you get to cosecant squared? Well, you start at negative cotangent. How do you get to negative sine?
Cosine.
Start at cosine.
I was thinking it was like a by parts.
I know. I don't know why. Sorry, I don't mean that. Other people were doing the same kind of thing. When you have functions separated by plus and minus in an integral, you can think of each one as a separate piece. You can think of it all together if that makes it easier, to be honest. But in this case, no way. Is everybody cool with that? Maybe? Sort of? Okay. This one, I saw somebody doing it pretty well. What did you guys do for part B or number 2? What method does somebody use? Anyway. Okay, by parts, did you get it to work? Okay. I don't think it would work. Yes?
U sub.
U sub. You have to use a form of U sub that some instructors don't necessarily remember to show. There's more flexibility with U sub than the base level. So for example, what part of the whole semester I'm going to be doing this, because that's the monitor I can see. It's the same shit up there, I'm sorry. Look at that, no. Now, if you're somebody who's sitting out there going, what the hell are you talking about U sub? If that was x squared, that would work, yes? U sub would work directly if there was an x squared inside, of course, yes? When the stuck piece has a derivative that's in there, U sub works directly. So this is going to be an indirect U sub U sub. U sub U sub. What would you let U equal? That's the greatest first step, is just, you generally, the first level of U sub is whatever's stuck inside of something else. Is it always that? Hell no. Is it often that? Hell yes. So what's stuck? X minus 1. All right, let's try it. U is x minus 1. What's du? Dx, okay. Now that does not help with this guy. But if I know u is x minus 1, what's x? Okay. Now some of you guys have seen this before. Some of you guys might never have seen this. I don't know. Because I know some people forget to show this when they're teaching this, but to me this is the immediate thing you show. All you have to do for u sub is replace all the x business with u business. As long as you do it legally, that's what you got to do. So of course you're allowed to do this, because that's replacing x with u, yes? So how do I now one thing is, I highly recommend, highly, and I've done a better job now, okay. When I was learning this, I never did the change of limits when I was in Calc 2. I didn't change the limits, or Calc 1, yes? What I did was I put them in parentheses, and at the end I brought x back, and then I plugged the 1 and 2 in. Trust me, a huge part of this class is going to involve things known as double and triple integrals. You're going to want as much practice at changing limits as you can get, because we're going to be changing the order of triple integrals, and you have to really understand how the limits change in response to that. Why would I ever want to do that? Because if I leave it, it's impossible. If I switch it, it's possible. Holy shit, motivation. I don't know if you guys are with me or not. So, how do I change the limits? And again, just to make sure everybody's with me, what do these mean?
X.
That's what x is doing. What am I about to have? A function, an interval involving u. So I don't give a shit what x is doing. I need to know what u is doing. So how do I figure out what u is doing? Well, u is always x minus 1. So when x is 1, u is
0.
holy shit. And when x is 2, u is 1. And what did we say x was? U plus 1. And what did we say x minus 1 was? Now, effectively what we've done is we've taken the two terms inside the radical and made it one term, which means we can now just distribute the damn thing. So another way to look at u sub is, for example, if you had a big mess on the denominator, don't you wish it was just one term instead of several, because then you could just break it up? U sub could do that. You start to, if I just let u equal the bottom, now it's going to work with everything else, but it could make the bottom become one term, and then I can break that shit up. You guys kind of follow? So it's a broader way to look at u substitution and the use of it. Maybe. You get some more. I'm always concerned about it. Some of you guys are like, first day, man. What the shit? Okay. So if I distribute, I'm going to get u to the 3/2 plus u to the 1/2. I want to integrate. 3 plus 2 is 5, so I get u to the 5/2, and then I put the reciprocal. 1 plus 2 is 3, and then I put the reciprocal from 0 to 1. I have an eternal battle with the number 3. And this is beautiful. Bodacious. You plug a 0 and you get nothing, so that's beautiful. Be really careful. Your e's to the, when you plug a 0 and you don't get 0. So if you're really careful, just assuming a 0 plugged in is nothing. When you plug a 1, you just get 2/5 plus 2/3. Which is?
16.
Yes. 16/15? Yes? Okay.
Wait.
I am.
Oh, never mind.
Is that all right? Does anyone remember or know how to check this in your calculator?
Can't you just plug in intervals and like a TRE for?
Yes. Well, you can put this into the graph, and you can do second calc number 7 is interval. So, did I bring? Look at me go! All right. So just very quickly, maybe. No. Give it a brain. It's at. Oh no. Let's see if I can do this. No, Jeff, you don't want to do statistics. So what is it? X times square root of x minus 1, right? Okay. And I want to integrate that. So second calc number 7. And I want to go from, oh shit. Come on, do it before your battery dies. Poor little guy. He's not liking life. That's taking way too long. Oh, I'm in a weird window. Zoom 6. Is that part of it? Okay, there we go. Alright. So then I can go second calc 7 from, what was it, 1 to 2 originally? Yeah, 1 to 2. Shabbat. And of course, then you just compare it to 16 divided by 15 to see if it's the same thing. 1.0666. Okay. 16 divided by 15 is 1.0666. Okay. Now on screen, it's going to sometimes not be able to resolve it perfectly, but it's pretty good to get an idea if things look right. Okay. Yes, okay. Alright. Did somebody try this a different way and have it work? I wouldn't think so, yes?
I just put multiplied x in there. X to x
Oh.
over 3 to minus
So,
x to the 1/2.
Big
Mine works.
from the beginning?
Yeah.
Mine
So a big problem with that is you can't, what would you have to do before you can multiply? You would have to apply the power, and the power can't distribute.
I did it a different way and it actually worked. I'm shocked.
How did you do it?
I did the integration by parts.
By parts.
Or I don't know. I just said u was x, and then I said dv was square root x minus 1 dx, and then I did the whole thing and I got this answer.
Okay. Oh, that would work. Yeah, okay. Just, I didn't really want to think about by parts, to be honest, but I appreciate that. That would work, yeah. Kick ass. Okay. Alright, and now of course I'm dredging up old trig stuff. So tell me anything that you need to know going in to figuring this out.
Unit circle.
Unit circle. Specifically about this, what are you curious about? What's true about the angle? It's in the... There's only 4, so you got a
Part of the circle.
25, 25, 25, 25 chance. It's in the third quadrant, right? Because it's how far past the pi, which is the dividing line between second and third. It's a third of a pi past the whole pi, so it's in the third quadrant. Is that cool? Third quadrant, which means secant would be, because secant's related to cosine. S goes to C, C goes to S. So it's going to be what sign? What SIGN? Negative. So I know it's going to be negative. I know the reference angle is... What's the reference angle? How much past pi did we go? A third of a pi, yes? So now I've rewritten my problem in terms of a basic value that I should have memorized, the cosine of pi over 3. And the way I remember these is cosine likes x, sine likes y. So the further I am from the x-axis, the smaller x cosine gets, and the bigger sine gets. So I just got to remember the value. So it could be 1/2, or rad 3 over 2, or rad 2 over 2, all kind of bullshit, yes? So I'm currently at pi over 3, which is 60 degrees. I'm very far away from the x-axis. Cosine is scared. So it's going to be a small one, little turtles going in a shell. It's like, oh shit. So what's cosine going to be? 1/2. And 1 over 1/2 is 2, so you get negative 2. Is that alright? Now some of you guys are like, let's put in my calculator. Shut up. This one, I think, had people going for a couple reasons. First off, the negative one's not a reciprocal, right? It's an inverse function. Does anyone remember how to do this problem? Okay, real quick. You did?
I did it as like a triangle.
Beautiful. So, that's perfect. That's all I had to say. I'm with you. What do you put into a trig function? Well, it's got to be true about the thing you put into a trig function. It must represent an angle. Must represent an angle, correct? Okay. That's the only thing trig functions work with, is if you put an angle. Now, you could think of it as a number or whatever, but it's some kind of an angle. Therefore, this is one way to get to this. The inverse sine of 1 over x is an angle. Is the angle where what is true. So if I say, this is going to take a while to get the concept in, and then it's going to be really straightforward to just do the work. That is an angle, yes?
Yeah.
If I take the sine of both sides, I get 1 over x is sine theta. Can you draw the triangle where that's true? Because that's what this says must be true. A triangle, a right triangle, where the sine of this angle is 1 over x. What side must be 1? The y side. And what sine must be x? Hypotenuse, because that's what the freak sine is. How do I answer the question it's asking? Because now I've set up a picture that visualizes what the shit this is, and now it just wants me to know the tangent. So what am I missing to figure out the tangent? this side. And what's that side going to be?
X squared minus 1.
Beautiful. Hypotenuse squared minus the leg squared. So what's the tangent then? Yeah, 1 over. Yeah, that's fine. You don't have to rationalize that. That'd be insane. Very quickly, can anyone tell me what must be true about x for this to make sense? At least for this to be real valued and works well in our number system. What must be true about x? See? Okay, greater than 1 or less than -1. So the absolute value of x must be greater than 1. Why? What output for sine has to be at most? Output for sine is at most 1 and at least -1. Therefore, the input for its inverse function must be at most 1 and at least -1. Yes? Therefore, the denominator must be greater than or equal to, I guess, 1. So the way to say that, or less than or equal to -1. Yeah, I love you guys so much. I know I added extra onto the problem, yes? But too bad. I can talk about whatever I want to. So that's a little thing. Whenever you have variables inside of your trig functions that inherently could pose a restriction on your domain. Okay. This one is the one that's the quickest way to bring me to tears. So if you put 2x plus 4, please keep it to yourself and don't ever. So, can you guys, I don't know if anybody, you don't have to fess up to doing that. Can you see why somebody would say the answer is 2x plus 4? Well, yeah, you're like, come on, Joe, what the hell? The square root of 4 is 2, square root of x squared, square root of 16 is 4, let's go home with the shit. What's wrong with that? Okay, you're missing a middle term. It's not truly something squared, but
Square it won't get you the same answer.
if you square it, you won't get the same answer. Beautiful, because that's what you said. But more fundamentally, a square root can't distribute across addition. What are square roots based on? Square roots are exponents. Are you guys with me? Because it's 1/2 power. So what are exponents based on? What operation? What operation are exponents based on? Multiplication. Therefore, they will not play well with addition and subtraction because they're not based on that. Yes? So I can't distribute an exponent across a plus or minus. And that's effectively what you're doing if you take the square root of each piece. You guys? Okay. Normally this leads to issues in Calc 1 and 2, but anywhere you do this shit, it's going to lead to issues. You're never going to get the right answer. So what can you do? There's one thing you could do. Take out of square root of 4 is 2. Square root of x squared plus 4 is, I don't know. And that, of course, is something I call simplifying the radical, where you take the part you can and leave the part you can't. Like the square root of 50, right, is 5, square root of 2, that kind of business. Okay. How are you guys feeling about that? Is that all right? We needed that shit, Jeff? Never do that again? All right. Okay. So, what I want to do is, any questions from this whole thing before I move on? Yes?
Can I just see 2B?
Yes. And by the way, there was another way to do it. You could do it by parts. All right, so I want to try something out. Never done this before, so this should be exciting. I want you guys to help me out. You guys, all right, let me see. Let's see, how's this going to be the easiest for everybody? Yes, okay. Bless you. Does anyone, if I ask anyone to stand up, would anybody not want to do that? Okay, could you stand up? Could you stand up? Yes. All right, don't worry, you're not in trouble. Come on, son. No. All right, just go with me for a second. Okay. Their heads, think of them as points, yes? Can you imagine, you guys are the points, this is crazy. So your heads are points. Can you imagine there's one line, of course, that goes through those 2 points, of course, right? So far, this is amazing. Thank you so much, Jeff. All right. We can also consider you to be the original point and you to be the end point. So that would be the idea of a vector, correct? I don't know how much you guys have worked with vectors. We're going to work with vectors a lot this semester, but all a vector really is the line segment where I define direction. So if I just connect their heads with a line, that's a line segment. If I say you're the original point, you're the end point, now it's got a direction. And it's got a length, of course. And if anyone's ever done vectors, you all know it's got a freaking direction and a length. Okay. Stay sane. Sorry. You need to sit down with me. Can you in the back stand up? All right. Now, I forgot I was going to ask you guys to tell me who to have stand up, and that's okay. I'll be all right. If I connect these guys with a line segment or even a vector, and I connect these guys, so you're the origin point. Just remember this for your whole life, right? You're the origin point of this whole thing. What angle does it look like I'm attempting to represent there? Right angle. I love it. So what's one word for that? No. I haven't connected these guys at the end. Perpendicular. I love it. So this semester we're going to learn, for some reason, a ton of words that all basically mean perpendicular. It's going to be exciting. Right? We got orthogonal, orthonormal, we got all this kind of stuff. Oh shit. Okay, now, stay sane. Sorry. These guys right here. There's only one line that goes through them. Yes? Okay. And these guys here, there's only one line that goes through them. How many planes go through them? So there's one line, is everybody with? There's one line that goes between their heads. Yes? Okay. Obviously, like, there's this plane, like here, right here, this plane goes through them. It's a little bit tilted, right? Because they're not the same height. Are you guys kind of with me? Yeah. Okay, I like it. Now, how many planes though? What about this plane that does like this? So can you imagine the line connecting their heads? Has anybody ever seen a Rolodex? Sorry, guys, stay standing. If you need to sit down, let me know. Anybody ever seen a Rolodex? This is like from a long ass time ago. It used to have a centerpiece, and then you could flip these little index cards. And it's back before we even had Palm Pilots or whatever. You had to put it on freaking. Oh, look at that! Let me roll it. All right, so I have a plane. Everybody, can you guys imagine the plane? You're a little shorter, right? So the plane is a little bit tilted, yes? Or I could have one come like this. So I have this whole selection like this going through their heads. There's an infinite number of planes that contain both of their head points, yes?
So you just draw a big sheet on all of them.
Yes. So I can have one that's going straight. I can have one that's coming out like this. I can have one that's coming out like this. Okay, maybe. Now.
It's like a shell.
Oh, okay. Sort of. Yes, so you can imagine a spine down the middle and all these connections going around. Okay, I like it. Now, if I introduce his head point, which is a very strange phrase, but we're going to be okay. How many planes go through all three of their heads? One. There's only one plane that goes through all three of their heads. Yes? I really want you guys with me. How many lines go through these two heads? One. How many points go through his head? One. One point. The point that is his head. Yes? How many lines go through these two heads? One line. Is there any other lines that exist that would go through both of their heads? Just that one, correct? If I had 1 point, how many lines go through his head? Infinite. I really want you with. This line goes through his head, right? This line goes through his head. This line goes through his head. Yes? This line goes through his head. All right. I really want you with. You guys with me? The minute I introduce a third point, just like if I have 1 point, infinite lines. Second point, definite line. 2 points, infinite planes. Third point, a single plane. There's no other plane besides this one that goes through all three of their heads. Correct? All right, I like it. You guys sit down. I'm sorry. I don't know if that was good, but we all know that it takes 2 points to define a line. Now you kind of understand, and it kind of makes sense. It takes 3 points to define a plane. Now, what must be true about those points? So if I had you, and you stand up, you still would define an infinite number of planes because you all are on the same line. So you have to have another point that's not on the same line that defines a plane. Are you guys kind of with me? Okay, maybe a little bit? Okay. All right. one of the hardest things about this class. Oh no, when did this happen?
That's a bit that noise down earlier.
Hardest things about this class, which is now a lot easier than it used to be, is visualizing what's going on. When I took this course, I had a teacher that was worse than me at writing. So when he would draw, there's no way in hell. We had no idea. But there was no Wolfram Alpha, there was no GeoGebra, there was none of this shit. So there was nothing we could go to kind of draw these things for us. Now we have a ton of stuff. Okay.
Desmond's gotten into it now.
Desmos can do 3D.
They got a new one.
Kicks so much ass. So I've put the links in Canvas. I haven't made them active yet. So I'll probably do that today so you guys can play around. So I know most of you guys know about Desmos, yes? Desmos is silly. If you just put, I've got the link. I think it's just if you put a /3D, then you go to Desmos 3D. And then it can handle functions of x and y. So you can say z equals x squared plus y squared. See what the hell that thing looks like. Right? Okay. So let me ask you this. So we have that little exercise there. Hopefully that did good. I don't know. We'll see. It's the first time I ever did that. Let me switch over to this. So I want to kind of do something a little more direct, but still isn't quite calculations of things. Help me out here. If I have x equals 3. So in one dimension, that would just be the point 3. Okay, that's fascinating. Now, what about if it's x plus 1 equals 3? Well, that would just be what? What would that be? That's insane. That would now be at 2. It's insane, right? And then, ooh, get ready, kids. X plus 2 equals 3. That would be, holy shit. Now, I know, this is groundbreaking. You're all like, oh my God, I gotta tell everybody. Here's what's really going on. If I have x plus y equals 3, what I've done is I've introduced a second dimension to move around in, right? And this is, again, this is not the most useful way to look at this when you first learn lines, but now that we're starting to develop math in a dimension we're not used to working in, we want to take a step back and analyze things we've already done in a different way. Okay. I want you to really be with me on this journey. So, I have established this is the x-axis. Now, where did we put the y-axis? True, but very specifically, how must it be oriented? It must make a 90-degree angle. We decided that our axes that we build points off of should be perpendicular to each other. You guys, that makes more sense. We could have, there's nothing that would have stopped us from having an x-axis and a y-axis like this. I could still create every point in the xy plane. It would just be more difficult. I need you to really be with me on this. Why is this easier? Because this controls up and down only, and this controls left and right only. The minute I do this, shit. This controls up and down and a little bit of left and right, and this controls left and right. I don't know if you guys are all with me. We didn't have to do this, but it certainly makes it easier to combine values on here to get a value in the middle. You guys semi with me. And again, I wouldn't blame you if you never thought about that ever. But we need to start thinking, why did we choose this to be a 90-degree angle? Because we could build other points easier. I have specific things that only deal with one dimension or the other. Okay. So, if I do this, if y is, stop it. If y is 0, where am I at? I haven't gone up or down at all, and x is 3. If y is 1, now my number line is now sitting at y equal 1. I have a literal number line sitting at y equal 1, but now my x, of course, is
2.
so I have this number line sitting here, and x is now 2 on that number line. And of course, I could do it for y equal to 1/2, y equal to 0.783477772. I can do it for all the values in the middle. There ain't no damn way in hell I would teach an algebra student this when I'm teaching them how to graph a damn line. That would be bullshit. But again, why do I necessarily want to go back and kind of like look at all these? Because we're about to extend into the third dimension that you guys are not used to working in. You're used to walking in it, used to living in it, but you're not used to doing math in it. Okay. So of course, if you keep going, you'll get the line. It's amazing. Ooh, it's amazing. Now, if I want to introduce another dimension, what must be true, continuing the choice we made? When we had an x-axis, everybody was happy. We're like, yay, what the hell? You don't need shit. What are you talking about? And then we're like, no, we need this way. We won't be able to rotate, man. We made it right angle to what existed already. Now we have an xy plane that exists. If I want to introduce another dimension, I need its main axis to be. What are you trying to do?
I'm trying to make you.
Yeah.
You're making obscene gestures at me.
It's like, this.
Like this, Jeff. Oh shit. No, you're good. Huh?
Like that, then it goes in like that.
So yeah, so imagine the easiest way to do this in the classroom is, and too bad if you're at home, you know. No, I can move this, but I don't want to. No. Did I even bring? No, it's fine. I didn't bring a single. Jeff is a teacher. Okay. No, I did not. Wait, do I have? I thought I had one.
Do you need a marker?
Yeah, I need like a whiteboard marker.
I've got one.
I have a Ghibli thing that I keep forgetting to put in. You do? Look at you, man. Look at that. Brownie points. Okay. So I have a XY plane. Now, of course, this stuff you know. Because I always tell this to my students back when we legally could teach algebra in community college, and I taught them about graphing points, I would bring into play the third dimension. Yes? So I know you all know already, if I wanted to graph the point 3, 2, 1, I would go 3, 2, 1. It'll be right there. So it's very difficult to make that point. If you needed to do that by hand, do you know how you would do that? There's something called, and I'm gonna bring some of this next time, because we're gonna do some of this by hand. Isometric graph paper.
Oh, so I got this right.
We're not gonna do a ton of graphing 3 dimensions, but we are gonna do a bit, because you only understand something if you actually have to do it. Yes. There's a lot of software that'll do it for you. Whoop-de-doo. So we're going to do a little bit, not a ton. It's going to be disgusting as hell to try to graph z squared equals 4x squared minus 7y squared. I'm not going to make you graph that by hand. That's insane. But you are going to have to graph a few things by hand. Okay. So obviously here, where would I put the z-axis? I kind of gave it away already, but you know. And it's basically what I think you were trying to motion. I've already got ground. This is the ground. Is there an axis that is perpendicular to the x and the y axis?
Yes.
I have to, of course, shoot out of the paper. Now, it's really, really neat. There's something called the right-hand rule. So if you there's a lot of variations. So if you take in physics, there's actually at least 2, if not 7, variations of right-hand rule. If you put your palm in the direction of the x-axis, and you curl in the direction of the y-axis, it'll show you which direction should be the positive z-axis. So that's the right-hand rule. That actually, how many guys understand that when I said curl and I said it in a different way, it's because it relates to a mathematical process. I can't remember if by now, if you've taken, how many guys have taken linear algebra already? Anybody? You have? So you know about the curl. You're like, I don't know. All right. So you might have heard about the curl versus the dot product. Does that sound familiar? Okay. If not, it's okay, because that's like one of the big things we learn in this class. So you're in the right place if you want to know. Okay. Is everybody with me? So there is one axis that is perpendicular to both of these. Well, this axis is perpendicular, but it doesn't really agree with where we want the origin to be, right? So you really want to get down to it. There's an infinite number of vectors that would be perpendicular to both of these, but this one has 0, 0, 0 as the ultimate origin. Okay, I like it. Isometric paper basically does, let me see. I suck at making this thing. Oh yeah, it's just this. Oh my God. You could Google and pull it up. No, sir. Basically does this, but in a better way. If you try to do this by hand by creating your own axes, that really sucks pretty quick. Okay. Especially if I tried it. All right, how are we doing so far? So a lot of what we've done in 1 and 2 dimensions has an immediate analog in third, just like we did the sphere. The formula for a sphere is exactly the formula for a circle, just with one more z plus or minus something thrown in. Now, linear algebra, which we're not in, so I'm not going to teach in this class, goes to however many dimensions you want to be. You kind of with me? Real quick, has anyone ever heard of a service called Pandora? Most of you guys know Spotify, but there's another one called Pandora Music, yes. Pandora was created by math people who happen to like music. Just bear with me for a second. They identified, for example, jazz music. They identified 500, roughly, characteristics of a jazz song. So when you said you liked something, you like a jazz song, that exists on 500 dimensions. Now very quickly, before I do all this, do you all agree with me that if we measured the temperature really precisely at every point in this room, it could be very different from this point to that point? You all agree? That is an example of 4 dimensions. Aren't there 3 physical dimensions in this room? Could I identify a dimension as, I don't know, 3, 4, 5? And then the fourth component would be the temperature at that point, correct? So very often, how you see that, you see it as a color gradient. We represent a dimension that we can't represent physically, we use color for it. Are you guys with me? So you see temperature gradients very often as colors. Because we can't do the 4th dimension physically. Yes? So the idea, I love you guys so much. The idea that we have things that can be represented in more than 3 dimensions is fine. There's not a damn thing wrong with that. Every day we deal with shit that deals with more than 3 dimensions. Are you kidding me? They just have to have more than 3 variables. Are you ever involved in a situation where there's more than 3 variables? Any time in your whole life? If not, that's neat. You only ever have exactly 3 things to worry about. That's neat. Not sure how that works. Conservation of things to worry about. I don't know. New rule. Are you guys all with me on this? So we're going to focus on 3 dimensions. Obviously, sometimes we'll fall back and do 1 and 2 because they build up to 3. It's amazing. We're not going to do anything in 80 dimensions. But just to show you, the math doesn't care. What if I had a 4-dimensional thing that whose shadow is a sphere? What would its formula look like? X plus a squared plus y plus b squared plus z plus c squared plus w plus e squared. Yes? You just keep adding another dimension in. Can you draw that shit? Have you guys seen attempts at a hypercube?
Yeah.
So it doesn't really cut it, but it's an attempt. Because 4th dimension physically is insane to try to do. Because okay, sorry. I'll stop, sorry. Okay. Where did I put my, there you are. So stepping back a bit. If I have a point, oh, what's happening to you? Here we go, that's fine. There we go. Ooh. In 3 dimensions. So I have a point, let's say, so this will be the x-axis, the y-axis, and the z-axis. So if I have a point, let's say 3, get out there, 2, let's say 3, 2, 4, roughly. 3, 2, 4. It'd be more over here, Jeff. You could do it, buddy. Okay. So you can see how horrible it is to try to do this without isometric graphing. I could look at the projection of that point in the xy plane. So this is the point. What did I just say? 3, 2, 4, yes? So I go 3 in the x-axis, 2 in the y-axis, 4 in the z-axis, right? Okay, I like it. What would the projection of that point be in the xy plane? If I shone a light directly perpendicular to the xy plane, where would the shadow be in the xy plane? 3, 2, 0. Yes? All right, where would the shadow be in the xz plane? What did I just say, xz? I can do it. Yeah, 3, 0, 4, and of course the yz plane, 0, 2, 4. I love it. You guys, does that make sense? If I shone a flashlight straight down, because my xy is kind of like my floor there, the projection, the shadow would be at 3, 2, 0, because it would be on the floor. Yes? Okay, maybe. Okay, I love it. I love it.
I'm not understanding how you did the graph with the point.
Oh, it's horrible. I did a horrible job. I'm really sorry about that. So if I want to graph 3, so I go 1, 2, 3.
I can't, because I can't see where you're pointing on.
Oh, very good. Very good. I have a laser here somewhere. Let me remember. It's up here. So, ooh, is that a laser? No, that's highlighting.
You just had a different color.
All right, here we go. Let me try this. Hold on. Everybody hold on to your butts. Okay. So 1, 2, 3. And then over 1, 2. And then up 1, 2, 3, 4. So it really should be more over here. I was right in the first place. But all right. Isometric paper lays out where you can just graph. In fact, let me do this. Let me Google, show you how you can get your own isometric paper. If I would have thought about it, I would have brought some. No, I didn't want to do that. Stop it. Take me to Google. Let me Google. Okay. So isometric graph. There we go. This will be fine. Blow up. No, blow up. Become a thing. You suck. All right. Zoom. Oh, it'll only zoom so much, and then it gives up. Okay, that's fine. So then you can see you can do your x, your z, your x, and your y. And then it's a little easier to kind of follow each axis as you're trying to graph points.
So the z-axis.
Perspective is, if I gave you a graph that had a point on it, there's no way in hell you could tell me what point that is. Because you're like, is the point close to me? Is the point far away? If it's close, do I just make it really big? You guys kind of follow? That is hard on a two-dimensional piece of paper to try to graph something in 3D and have somebody else tell me where it is. I can't show depth of field with that very easily, right? There's no slider in my, let me go to my settings. Nope. Shit. You guys kind of with me? So I would never give you a problem where I have an already graphed point and say, what point is this? It could be quite a few different points, right? So if I have a point, you see where, oh yeah, it's here. So this point right here, that point that just disappeared, because I forget if I do it, it'll erase. That point could be right next to it. So it could be x is 50, x is 50, y is whatever, and then z, it could be like right in her face, or it could be like way down. It could be way down. I don't know if you guys are really with me or not. This is why we use software very quickly. I need you to get practice with trying to graph these things, but you can see how difficult it is to show somebody where things happen. Especially if I have to graph like an actual function. And they end up being these sheets that move along. And maybe in a minute I'll show you a three-dimensional grapher, because it's really, really cool. Oh, that's right, we're almost done. Shit. Sorry. Okay. Where was I? Oh, okay. There's an idea called a Cartesian product. Has anyone ever heard of this before? So a Cartesian product, very quickly, if I have a set A, B, and another set C, D, the Cartesian product of those two sets, which is just where we get our time symbol from, would be all these sets that all the points I can create where A is the first coordinate and C is the second coordinate. So this would be the set A, C, A, D, B, C, B, D. So is A cross C the same as C cross A? No, so immediately we can see it's not commutative.
I think we read this in algebra. We just don't know.
Understood. How many elements are in that set? 4. And how many elements are in each of these sets? 2. So 2 times 2 is 4. So we stole the idea of basic multiplication from the idea of Cartesian product. If I take, now, you guys know what this symbol means, yes? What does that symbol mean?
All real numbers.
All real numbers. If I take this, what do I get? So if I take, give me a real number. 1, give me another real number. 17. Okay. Now do that with every possible combination. What do you end up with? The x, y plane. Bless you. This is, remarkably enough, this is r squared, which is the symbol we use, for example, the x, y plane. Now, it could be the x, z plane or something else, but anything that has just 2 coordinates that really define a position in it.
So it'll just tell us how many, or what plane we're working on.
Say again?
So is it just gonna tell us what plane we're working on?
This is notation and why we use the notation that we do. Because I don't know if anybody's ever seen this notation. I think some of you guys probably have. So how would I construct 3-dimensional space? R cross R cross R, which means just make all the possible 3 coordinate points you can, which is r cubed, which just is our normal octant of x, y, z stuff. Right, so x, y is got quadrants. X, Y, Z has got octants. Yes, there's 8 parts you can create from you guys got it with me? Yes, maybe a little bit? Yeah. Yes, okay, beautiful. Positive x, positive y, negative x, negative y. Positive x, negative, positive z, positive, blah, blah. So you can make 8 octants instead of 4 quadrants. Okay. The last thing I want to talk about how you did that. I did that. I love it. I did all of that. I think that might be enough. Yeah, I think that's probably enough. Oh, yeah, we're almost there. We're almost to the next section. So we talked a little bit about section 12.1. We're going to finish that up next time. We'll get into the vectors next time. If anyone has any questions or anything, just stay after. Otherwise, I think we're done at 2:35. Is that right?
Yes.
So I'm letting you out like a whole 5 minutes early. Oh, my God. Don't use them all in one place. Let me know if you have questions. Otherwise, I'll see you tomorrow. If you need an ad code, come up and see me. Oh, don't let me steal this. This is yours. I appreciate that.